Today we're going to look at Euler's method. It's not Euler's method, it's Euler's method. If you say Euler's, I'll slap you. No, I won't. I won't do that. I'll get fired. So, Euler's method. What is Euler's method? Euler's method is a way to numerically approximate values of a solution to a differential equation without actually having that solution. What does that mean? It means if we have a differential equation, we can approximate values of its solution by using this method. Still, maybe you don't know what that means, so we should take a look at an example. So use Euler's method with 3 equal steps to approximate f of 2, so that's what we're looking for, f of 2, given that dy dx equals that, and the initial condition is that. Okay, let's unpack this stuff, because there's a lot of things going on. First, we have a differential equation. There we go. And we have an initial condition, which means, remember, if I drew like a slope field, you don't have to write this. If I drew a slope field and I had a whole bunch of slopes, like pointing somewhere, and then I had some initial condition, remember that would say that I would have one specific solution. I mean, I guess this is not actually a solution, but if I had an initial condition, that guarantees that I have one particular solution, rather than a whole like family of solutions. So, still, I don't know what that solution is. Remember, solutions to differential equations, solutions to this are functions. So the actual formula for y would be the solution. Here's what Euler's method does. It allows us to figure out f of 2 without ever, actually, it allows us to figure out an approximation for f of 2 without ever actually having the function definition for f. It never like we don't have a formula for f. But we can figure out an approximation for f of 2. And that's because we have an equation that for the slope. So we can just start plugging in stuff and it'll get us kind of close. So real quick, what do I mean by that? Well, here's what's going to happen. So this is, you don't have to write this down. Pretend that I knew this, wait a minute. There we go. Pretend I knew what f of x was. So pretend that that's actually my function. Suppose I knew that. This is like the red part is stuff that we're pretending about. We don't actually know it. But I know, given the initial condition, that when I plug in -1 to this, -1, I get out +3. That's why. So I know that the graph goes through that. And I have a formula for the slope. So if I plug in -1, and I get out +3. So here, if I plug in -1, what slope do I get out? Well, before I actually get that, why am I doing that? What I'm going to do is I'm going to pretend that for one step, for one unit, that the slope is constant. Instead of, like here, the slope is ever changing. You can see it because it's a curve. But I'm going to pretend that from here to here, I have a constant slope. So I'm getting an approximation for this function. So I'll get whatever slope. Pretend it's like 3 or 4 or something. I'm guessing on this, so it's not actually going to be what it is. So pretend I plug stuff into here, and I get a slope of, let's just say 1. I get a positive slope of 1. So that means to get from this point to the next point, I would plug in, well, I move over 1, and the slope is 1 over 1. I'm pretending that that's what I got when I plugged it in. I'm pretending that that's what I got. So then I would go up 1 over 1, and I'd land right there. I mean, it might not be exactly on the function. Let's pretend that it's not exactly on the function. And now I have another x value. I have x being 0, and I actually have another y value as well. So whatever y value that is, looks like 4.2 or something. I don't know. That's also pretend. I got there by using the slope from my initial conditions. I plugged in -1 and 3 and pretended that I got 1. Then what I would do is I would plug in 0 and 4.2 to my differential equation and figure out another slope. And then I would follow that slope from here to the next spot. Maybe I don't land exactly on my function, but I'm getting something that approximates my function. That's the whole idea. And I can keep doing that. Oh no, I can keep doing that for as long as I need to. The approximation will probably get worse and worse, but it's still an approximation for this function. We can actually just go by smaller and smaller steps to get closer and closer. So that's what we can do, and hopefully that makes sense. But now I'm actually going to do the problem. So I'm trying to get first step. Well, maybe you should write this down. Like, pay very, very careful attention. If you write this down, everything will be super easy. So the first thing that I'm going to do is I'm going to make a chart. And I'm going to start with my initial condition. I'm going to have an x value of -1. My y value is 3. So what is dy dx? Well, I just plug it into there. Easy enough. I feel like a lot of people are going to miss what I just said, even though it's a video. How do I get dy dx? I plug x and y into my dy dx equation. And I get -7. Again, how do I get this? I plug in x and y to this. I'm going to say it again. I plug in x and y to my derivative function. That gives me a slope. So I have a slope of -7 over 1. So how am I going to get to the next x value? Well, it says, I mean, this is something that I haven't talked about yet, but it says use Euler's method with 3 equal steps. So right now, I haven't even taken the first step. But I want to approximate f of 2. Now notice this. I start out at -1, and I want to get to 2. Again, I start out at -1, and I want to get to 2. So, -1, and then all the way to 2. How many spots are in between that? Well, I could just do 2 minus -1. That's 3, right? I'm just finding the distance in between. I'm just finding the distance. I feel like so many people don't pause the video when they need to. So I'm just going to keep repeating. So I want to have 3 equal steps. 1, 2, 3. So -1 to 0 to 1 to 2. That's 3 equal steps. So I'm just stepping by a unit of 1 for my x value. Hopefully that makes sense. I really hope so. How do I get from -1 to 2? Well, it tells me to use 3 equal steps. So I just go -1 to 0 to 1 to 2. That's 3 steps. So that's how you do that part. So I can just fill this in right now. -1, 0, 1, 2. That's +1, +1, +1. Those are the 3 equal steps. I don't have to do equal steps, but this is telling me to do equal steps. So there we go. Do you understand? How did I get these numbers? It told me to use 3 equal steps, and I decided, well, to use 3 equal steps, I can just increment by 1. That's what you do. That's how you do that. Okay, great. Now, let's see. Since I'm incrementing by 1, and my slope, remember, slope is rise over run, which is the rise is like the y change and the run is like the x change. So that means for every one value, right, for every one value of x that I change, I subtract 7. I subtract 7 from y. Okay, so I go over to the right 1. I'm saying like I'm adding 1, like on if I have my graph. I'm adding 1 to the right, but that means I have to go down 7. It makes a -7 slope. Okay, so I run 1 for my x. I did that already. And for my y, I have to subtract 7. And I get -4. Great. That's fantastic. What do I do now? Well, again, how do I get my dy dx? I plug it into this. It's like I'm getting upset and I'm not even talking to anybody. So hopefully this makes sense. Hopefully this is not too long. It's too long. The video's too long. I'm sorry. If I plug it in, that gives me a slope of +2. That's 2 over 1. So every time I move to the right 1, I add 2 to y. Because that's just rise over run. How am I getting that? What the heck am I doing? I'm just looking at the change in x, and for every 1 that I move for x, that means I have to do the rise for the y. Well, that's plus 2. So I take negative 4 plus 2. That's negative 2. And then, how do I get my dy dx? I plug it in. This should not take you this long. I'm just reiterating things over and over and over again. And if I plug that in, wait a minute, I think I messed up. This part should have been something else, right? Because I didn't plug it in properly. If I plugged in 0 there, it would be 0 minus negative 4. Oh, no, that's fine. Okay, so let's see. When I plug in 1 and negative 2 to this, that gives me still positive 2. That's positive 2 over 1. So when I increment to get to 2, I have to add 2. So that gives me 0. And I think we've done it. F of 2 is approximately 0. Right? Because I plug in 2 and I get 0. It's approximately 0. Okay, there we go. There we go. Now we could plot a slope field and see if this kind of like works out if we start at that initial condition, but that will take too long and the video is already crazy long. Goodbye.